Hey, this is the coding teacher, and I'm back with a 5-minute LeetCode series where I explain a LeetCode in 5 minutes and then take however long it takes to solve it. Today I'm working on this one, validate a binary search tree. It's actually a relatively common interview problem. And we're going to start by looking at the problem prompt. They give you a binary tree, and you have to determine if it's a binary search tree. So a binary tree is a structure like this one, where there's a value, a left pointer to another tree node, and a right pointer to another tree node. A binary search tree has the added restriction that each node, if you look at each node, all the nodes to the left are lesser than that node, and all the nodes to the right are greater than that node. And this applies recursively at every node in the tree. There's also an alternate definition that includes that allows for duplicates, but that's not what they're going into in here. They're asking us to determine whether a binary tree is a binary search tree, and that's relatively simple. All you do is traverse, in order to traverse the binary tree, and then verify that the sequence of numbers is strictly increasing. So we're gonna go ahead and explain, because that explanation is so simple, we're gonna go ahead and explain what is in order traversal. So if you have a tree, let's say 5, 3, 1, 4, 10, 6, 15. In order traversal is an algorithm that basically says the base case is if the tree is null, return, right? Otherwise, traverse left, process current, printing it, adding it to an array, whatever you want to do, and then traverse right. Right? In the case of what we want to do, we want to add them to a list, right? So what this will look like is basically we're going to be returning a list comprised of all the elements. I spread all the elements when I traverse left, comma, then I have my current element, and then spread all the elements that come back when I traverse right. So that's where this is the basic gist of it. If it's null, if the tree is null, I return an empty array, right? And otherwise, I'm going to return the result of traversing left, spread into an array, comma, the current element, comma, traversing right. How does that work, right? So let's go into step by step. So we go into here, right? It's not null, right? So I'm going to return list that says traverse 3, right? So I'm just, this is pseudocode, this is not real code. Comma, the next element in the list is 5, and then the next element in the list are the results of traverse 10, the tree rooted at 10, right? So now, what does traverse 3 do? So now I come into here, right? So because programming language evaluate left to right, you can't even evaluate this 5 until you finished like evaluating this first statement right here. So this is really what's happening. We're going into here before we even get into the 5. So we go deeper into the hole with the traverse 3. So now we're looking at that, right? Is that null? No. So what does this turn into? So I'm going to erase it. And that turns into a list, right? Where I'm saying all the elements of traverse 1, comma, then the 3, then all the elements of traverse 4, right? Oh, I gotta spread them out, right? So now I go into the 1 here, right? And you could even have another base case here that if both children are null, then just return a list of the current element. And let's imagine that we have that, right? So because it'll make it simpler to explain at one less level. So then that returns a list of 1, which we spread out, and it just the number 1. And then this recursive call right here returns a list with the number 4, which we spread out. So it's simply the number 4, right? So that original recursive call turned into this list, which I spread out, right, with the spread operator. And now I have all those elements added to the main original top level return value. So now I finally get to evaluate the 5, comma, and now I get to do the same thing. Go into this traversal right here, and then add those elements. First evaluate the recursive call on this one, then evaluate the recursive call on this one, then evaluate the 10, then evaluate the recursive call on this one. And that's how come I end up with 1, 3, 4, 5, and then this turns into 6, 10, 15. And by the way, the other traversals are easy to remember. So remember what we had in the beginning. So in order was go left, then process current, then go right. So if you want to do pre-order, you just move this to the beginning. If you want to do post-order, you move this to the end, right? So pre-order, the current node goes in the beginning, previous to anything else. Post-order, the current node goes in the end, after everything else. If you want in order, then the current node goes in between the going left and going right. So it's relatively easy to remember, and that's 6 minutes of explanation. So let's go into the solving of the problems. First thing I'm going to do is function in order traverse root. I'm going to implement the in order traversal. If not root, return an array like that, return, and then in order traverse root dot left, and then root dot val, and then in order traverse root dot right, and should be good. And then in here I'm going to say const in order, or const so I don't want to call it in order numbers, because then, so like traversal results, they might not be in order if it's not a binary search tree. So traversal result in order to, I already had that copied, in order traverse roots, and then you could do a loop here, right, and check each element against the previous one. I'm gonna do a reduce statement, so return traversal result dot reduce, and my function is gonna be basically, I'm going to be returning true whenever the current element is greater than the previous one. So I'm going to, this is the gist of it, right? So I want to return the accumulator and some expression that's going to, it needs to take care of some edge cases, but the meat of it is, gotta add the index here. The current should be greater than traversal result IDX than the previous one. Okay, but this doesn't work for the first element, right? So I have to make this expression a little bit more complicated. So I have to say something like index is not index, IDX is equal to 0, or IDX is greater than 0 and this. I'm actually not even sure that I need this IDX greater than 0, but it's my accumulator and this thing. So let's test it like that. Let's see how that goes. Okay, so for 213 it worked. Let's see if it works here. False. So now let's turn this one. Actually, let's try with the null case first. Let's see what that does. I expect a true there. Yep. And now let's turn this into a real tree. So I have 514. So in order for this to be a real tree, this has to be greater, and this has to be all of these have to be greater than 5, and they have to comprise a tree themselves. So 4, I'm going to change it to 10. This one, something less than 10, but greater than 5, so 7. And then something greater than 10 and greater than 5. Here we go. That should be a true. Okay, so let's go ahead and submit and see. There we go. Rather inefficient solution, as you can see, but very simple to remember, very simple to explain, simple to implement. Your interviewer is not going to have a runtime, processor in their head. So what you want to do is be likable, get the implementation out, get it correct, and if it works, you're going to be hired. That's it for me today. I hope that was informative, and if it was, go ahead and hit like and subscribe, and I'll see you folks next time.